Okay, so a bunch of you have asked about combustion analysis. So I'm going to do a little presentation which I'm going to record and then I'm going to upload to Canvas, and hopefully you will be able to follow what I'm putting down here. First things first, we've got to recall that combustion is a fuel plus oxygen leads to CO2 and water. And that may balance any which way, but there's a couple of features which we have to take note of right now. The only carbon on the reactant side is in the fuel. Therefore, any carbon contained in CO2 is from the fuel, and it's a 1-to-1 ratio. The only hydrogen in the equation on the reactant side is from the fuel. Therefore, all of the hydrogen in water comes from the fuel. And there's 2 hydrogens in H2O for every 1 hydrogen in the fuel. Now, this is going to be really important when we go to do combustion analysis. So let's talk about what that is. Combustion analysis is when you burn the crap out of a sample and you turn it all into CO2 and water. And most of the time you have to use a catalyst to make that happen all the way, which is what that yellow thing is with the copper oxide. And then you put in a water trap and you figure out how much water you've produced, and you put in a CO2 trap and you figure out how much CO2 you've produced. So you get a weight of water and a weight of CO2, and you have a weight of your initial sample. So from here, we have 2 separate cases that could come up, but we have a general way of solving these problems. So we convert to moles, we use the general combustion formula, and then we determine the empirical formula. And I've linked to a YouTube video that has a pretty reasonable step-by-step explanation that is not my own. So if you need an alternative explanation, please use that link. But I'm going to go forward with mine. All right. So we always have to convert from mass to moles in order to be able to do these types of problems. So this is just a reminder. Let's say we started out with 24 grams of CO2. We would divide by the molecular mass of CO2. So that would be moles over 44 grams, and that would give us 0.55 moles. And this is just examples of how to do that conversion. Let's say it was water and we had 55.7 grams. We would then divide by 18 in order to get 3.09 moles of H2O. This is not a combustion analysis example. This is just, remember how to do this? Great. All right, so moving on. Let's say we want to determine our empirical formula and we have just carbon and hydrogen in the material. So we get to moles using the previous technique, and then we normalize the moles by dividing by the smallest number of moles, whatever that happens to be. And let's say we ended up with a formula that's like C1H2.5. We want to get to whole numbers for our empirical formula. So in this case, if we multiply by 2, we will get 5, because 2.5 times 5 times 2 is 5. So an empirical formula of C2H5. And if you have had chemistry before, you know that's not really a thing. So that's probably not the molecular formula. We'll get to that later. This is the easy version, where all you have to do is take the number of moles that you calculate, divide by the smallest number of moles, and use that ratio in order to get whole numbers by multiplying by a coefficient. What about the case where you have carbon, hydrogen, and oxygen in the material? So that thing where I said that the moles of carbon is the same as the moles of carbon in CO2, and the moles of hydrogen is related to the hydrogen, or the moles of hydrogen in the fuel is related to moles of hydrogen in H2O. Well, the moles of oxygen are clearly in both the fuel and the oxygen that you're adding in. So because of that, we're going to use a little subtraction problem. It's our little trick. We know the mass of the compound because we measured it before we burned the crap out of it. We subtract off the mass of the carbon that we can get from the moles of the carbon. We subtract off the mass of the hydrogen, and we get the mass of oxygen, which we then convert to moles. And I'm sorry, that's a typo there. That should be mass of hydrogen instead of mass of oxygen in the second subtraction. We then normalize the moles, and then we find the empirical formula. All right, so let's do an example of that. Let's say our compound weight was 17.471 grams, our CO2 weight was 25.612 grams, and our water weight was 10.477. So we convert from mass to moles, and then we use our mole to mole ratio in order to find moles of carbon. We know we have 1 mole of carbon for every 1 mole of CO2. That's in the formula itself. Then we multiply by the mass, or the atomic mass of carbon, and that gets us grams of carbon. And we need grams because we can't subtract off moles from grams in our compound weight. We do the same thing for water, except it's slightly different because for every 1 mole of water, we have 2 moles of hydrogen. So we actually have to multiply our number of moles of water by 2, and then we use the atomic mass of hydrogen in order to find that we have 1.1724 grams of hydrogen. So we take our compound weight, we subtract off the weight of the carbon, we subtract off the weight of the hydrogen, and what is left is the weight of oxygen. Because mass cannot be created or destroyed, this has to be true. Moving on. All right, so now we have a mass of carbon, a mass of hydrogen, and a mass of oxygen. We can divide by our atomic weight again for each of these, and we find the number of moles of each. Now again, we're going to divide by the smallest mole value, and we're going to find that we have 1 mole of carbon to 2 moles of hydrogen to 1 mole of oxygen. CH2O, it's a carbohydrate. Okay, at this point, we are probably done. This is an empirical formula. But if we had to determine a molecular formula in addition, we would go on this next step. So we would take the molecular weight that they would give us in the problem. So that would be 90.079 grams for this particular example. No, I haven't talked about this before. This is just an example. We would know the empirical formula of CH2O, which has an empirical formula weight of 30 grams. If you take the molecular formula, you divide it by the empirical formula weight, you will get the ratio that you need to use. So you need 3 times the weight in order to get to what you want. So you need 3 times everything in the formula in order to have the correct molecular formula. So CH2O becomes C3H6O3. So again, you divide the molecular weight that they give you in the problem by the empirical formula weight, and whatever whole number you get out, you multiply all of the coefficients in your formula by, and that will give you the molecular formula. If you still have questions, please email me or text me or get in touch with me some way. I hope that this helps you to figure this out. In the end, what we're talking about is using mole to mole ratios, mass, mole conversions, and doing simple multiplication and division with stoichiometry. So if it's still not making sense after looking through this and looking through that YouTube video I linked to, definitely get in touch with me. I will see you guys on Monday. So to summarize, combustion analysis is a quantitative technique that involves burning a sample and measuring the carbon dioxide and water given off. It can be used to determine the empirical formula of a fuel, fuel here being something that burns. So we convert mass of water and carbon dioxide to moles. We convert each of those to carbon and hydrogen using stoichiometry, 1:1 for carbon dioxide and carbon, 2:1 for hydrogen and water. And then we convert back to mass of the element. subtract the carbon and hydrogen masses from the sample weight to get mass of oxygen in the original sample. And finally, you convert the mass of each element to moles again, and then divide by the smallest number of moles in order to get the empirical formula. You can use the empirical formula with molar mass to find the molecular formula, which should be familiar even if it's been a little while, and not even that long, like last month.